In countless movies, a character holds a single lighter up to a ceiling sensor, and instantly, every sprinkler in the building activates, soaking the room in a simultaneous water dump. Real-world physics operate differently. Standard fire sprinklers are blind to smoke and independent of central fire alarms. They respond exclusively to localized, intense heat. An automatic fire sprinkler system functions as a decentralized hydraulic network of independent thermal sensors. Each head operates as its own autonomous trigger. This targeted design allows the system to neutralize a fire at its source. By activating only the heads directly above the heat, the network suppresses the threat while protecting the rest of the building from water damage. To see how this works, we have to look at the individual sprinkler head. This component serves two distinct roles. It is both a mechanical heat detector and a physical control valve. The most common trigger is a frangible glass bulb filled with a glycerin-based solution. As fire causes the ambient air temperature to rise, the liquid inside the bulb expands. This creates internal pressure that eventually shatters the glass, releasing the mechanical plug and allowing water to flow. Engineers use color-coded glycerin to indicate specific activation thresholds. According to NFPA standards, orange or red bulbs are rated for ordinary hazards and break between 135 and 170 degrees until the air reaches 500 degrees. Activation speed is determined by the Response Time Index, or RTI. RTI is a measure of the sensitivity of the thermal element in relation to the velocity and temperature of the fire plume. Elements with low thermal mass have a low RTI, classifying them as fast response for residential settings. Higher mass elements are standard response, allowing more time for multiple heads to open in large commercial spaces. When the water is released, it strikes a metal deflector plate. This plate is shaped to convert the high-pressure water column into a uniform hemispheric spray pattern designed to cover a specific square footage. The thermodynamic response of that single glass bulb determines the system's efficiency. It ensures that water is only deployed where the thermal threshold has been breached. The environment of a building dictates the piping architecture used. The standard is the wet pipe system. In climate-controlled spaces like this hospital ward, pipes are permanently filled with pressurized water, allowing for instantaneous discharge the moment a head activates. Wet pipe systems are vulnerable to sub-freezing temperatures. If the water inside turns to ice, it can cause the pipes to burst, leading to significant structural damage. For unheated environments like this warehouse, engineers utilize dry pipe systems. Instead of water, the pipes are filled with pressurized air or nitrogen. This gas pressure holds back the water supply at a heated valve room. When a sprinkler head activates, the air escapes first, followed by the water. High-value environments require a different level of security. In a data center, an accidental leak from a damaged pipe could destroy millions of dollars of infrastructure. These spaces use pre-action systems. These systems often employ a double interlock mechanism. A double interlock is a safety configuration that requires two independent events to occur before water is admitted to the piping. A separate smoke detector must confirm a fire, and a sprinkler bulb must shatter. In extreme hazard zones like this aircraft manufacturing floor, engineers use the deluge system. Unlike other designs, deluge sprinklers have no glass bulbs. Every head is permanently open. A central deluge valve is connected to an external fire detection grid. When triggered, the valve floods the entire hangar simultaneously, blanketing the area in water to suppress fast-spreading fuel or chemical fires. Selecting a system involves balancing the speed of suppression against the specific environmental risks of the building. Reliable fire suppression depends entirely on the availability of adequate water pressure at the moment of activation. This tracing represents the process of hydraulic calculations. Hydraulic calculations are mathematical determinations of fluid pressure and flow rate throughout a piping system. Engineers must ensure the water has enough energy to travel from the municipal main, through the fire pump, and up the building's riser to the furthest sprinkler head. Under NFPA 13, designers must calculate for the most hydraulically demanding area, which is typically the highest and most remote point. They calculate the necessary gallons per minute, or GPM, to control a fire in that specific zone. GPM is a measure of the volumetric flow rate of water. This zoom shows the Hazen-Williams formula in action. Hazen-Williams is an empirical formula used to calculate pressure loss due to friction in water pipes. Engineers account for this friction, along with elevation loss, to determine if the building requires a supplementary fire pump to boost pressure. Guaranteeing that a system performs as intended requires these rigorous calculations to be completed during the initial design phase. A sprinkler system's reliability depends on its physical condition, which can degrade over time due to pipe corrosion or valve wear. Strict adherence to OSHA 29 CFR 1910.159 and the NFPA 25 inspection schedule ensures these hydraulic networks remain ready for an emergency. If you want to learn more about workplace safety and OSHA rules, subscribe to HSEstudy. Modern fire sprinklers operate as highly specialized thermodynamic sensors. They rely on the predictable laws of physics and calculated hydraulic pressure to protect lives and property.